This is the second in a series of videos in which I'm attempting to repair this second Wren executive computer. In the first video I got as far as getting the system to actually start to boot, and it started up the self-test and it is failing on the second test. That test is for the video RAM, so that's the RAM down in this corner of the board, and it's obviously just trying to write values to the DRAM and then read them back. And the readback is of course failing. It's not getting back the values it's expecting, so it's throwing up an error. So I need to investigate this and find out why that test is failing. And the way I go about this, you've seen before that I will use a logic analyzer, attach that to various devices on the board, and then start fault finding that way. I thought I'd do something a bit different this time for a change, so I've broken out the 4-channel scope. It's not quite as easy to use as a logic analyzer for this, but it should give us some fairly good information. And what I did then was to start probing around the DRAM. Now, if you're familiar with boards like this, you'll know that fault finding on systems like this with DRAM, especially when you don't have a schematic, can be quite difficult, because there is quite a lot of glue logic around that's there to enable the refresh cycles on the DRAM to operate without there being a clash between the reading for the refresh and the read and write cycles that the machine itself is trying to perform on the DRAM. And a fault like this with a schematic is probably going to take you 10 minutes to resolve. Without a schematic, all bets are off. It can take a very long time to try and pin down exactly what's going on, because you have to figure out where each signal's going and what each signal's actually trying to do. But the way I go about this is I start at the DRAM, I probed around on the DRAM, and these are 4416 devices, and so what I do is just look at the DRAM, see what the signals are and if they're what I expect. And what I found was that all the signals seem to be there, although the write signal, write enable signal for the DRAM was intermittent. Sometimes it would appear when I pressed the reset button on the Wren, and other times it wouldn't. So that's kind of indicative of a failing chip rather than a failed chip, and they tend to be the harder ones to find, because if you look at them with a scope you might be fooled into thinking they're actually working. So what I did here is I used a multimeter in ohms range with the Wren turned off, found out where that particular line goes, and I couldn't really find anything wrong with it. It was going through and the control logic seemed to be doing what it should. I used the logic comparator to check the devices that were in the control path for the write signal for the DRAM, and that all seemed to be fine. So that then leads us to the possibility that possibly the second part of the test is failing and the first part is passing. So what I mean by that is there are 4 devices and they're in pairs. So there are 2 pairs here to give us 32K of video RAM, but they're in pairs. And what I found was that when I press reset on the Wren, the write signal to one pair was occurring every time, and that was sometimes followed by an intermittent write signal to the second pair. Now that could well mean that what's happening is that the data value is being read back as sometimes successful and other times not, and that tended to point to a problem with the data bus going into the video RAM. So I followed that back through, and it goes primarily to 2 devices. We have an 8-bit latch, and the 8-bit latch is there to allow the system to set an address for the video RAM, but then be able to go off and do something else without that address changing. That's updated through a buffer chip, and the buffer chip is the one that I have the test clip on. It's the 74245, so it's a bi-directional 8-bit buffer. And looking at the scope, what I have is the bottom green channel is the enable line for that particular device. The purple channel, second one up, is the direction control for that buffer, and then the blue is the output, that's channel B of the buffer, and the top yellow trace is channel A, or the input to the buffer. And the amplitude of the two top signals are both set the same. And if you're familiar with looking at systems like this, you'll probably already see there's a bit of an issue there. I'll do some single shot captures, and what you can see is that if you look at the various signals, the input and output are not correct. They're following each other in that the input and output are doing what they're supposed to, but the blue trace is nowhere near the right amplitude. It's kind of right on the threshold of whether it's going to trigger any TTL circuits or not be seen by them. So it could be the buffer itself, it could be the latch, which is what it's feeding into. I'll start by replacing the 245. That's it's a fairly common fault with this type of machine. The 245s do tend to get a lot of abuse in these systems because they are connecting different buses together, and especially if there's issues with the power supply, then they can get damaged. So I'll replace the 74 LS245. I'll put a socket in there, put a new chip in. We'll come back and we'll have a look at the signals to see if they improve. I've replaced the buffer chip, and as we can see on the scope, the signals are now much better. We're getting up to the amplitude we'd expect. Signals are also different. They're not intermittent as they were previously, and it does look more like what I would expect to see. However, the test is still failing at the same point. It's still failing on test 2. So I'll do a bit more probing around and see if I can find anything else wrong in that area. Quite possibly the latch is faulty as well. That may be what actually damaged the device in the first place. But I'll have a look around, see if I can find anything else, and then decide what needs to be done next. So I've been tracing around the board trying to figure out why the test is still failing for the video DRAM, and I've got back as far as this device. It's another 74 LS245 buffer chip. I've got exactly the same setup as I had for the first one in terms of testing, and if I do some single shot captures, we can see that it's not doing what it's supposed to. The purple trace is the direction line for that particular device. The green line at the bottom is enable. It's enabled low, so it's enabled all the time. And the top two traces are the A and B inputs outputs for the buffer. And the way the buffer works is it transfers data from A to B or B to A depending on the state of the direction line, which is the purple line. And when the line is high, then whatever is on the yellow trace should appear on the blue trace, and vice versa. Whenever there's something on the blue trace, it should appear on the yellow when the direction is low. And obviously that's not happening. There's nothing happening. There's no output on the B channel at all on this buffer, so I'll get this replaced and we'll come back and see if we've made any progress. I've replaced the buffer chip, as ever, put it into a socket. The data bus now looks fine, however I'm still getting the same failure, so that's still fault 2 showing up, which is the DRAM fault, of course. So rather than just keep searching around the board randomly looking for faults, and because I don't have a schematic, then the next easiest method is to either switch to the logic analyzer, or in this case what I'm going to do is actually pull out the Fluke. So we'll get the 9010A connected to this, and what I'm trying to do now is to isolate the issue with the DRAM. So rather than trying to pull out the signals that relate to the DRAM from everything else that's going on with the board, because obviously we've got the refresh, we've got the other activities that the microprocessor is running, we can stop all those, attach the Fluke and do nothing but write or read values to and from the DRAM. So what I've done is hooked up the scope. So again, I've still got the 4-channel scope hooked up, and what I'm monitoring here is the actual DRAM chip. This is the first DRAM chip, And if you recall from previous videos, in this machine the DRAM is mapped partly through the range 8000 hex, and that's what we'll use as the target address, because I happen to know that this chip is mapped into that memory space, and because we know that, it means we can write values directly to it. So I'll get the Fluke connected, and what we can then do is start looking for information being directed towards those devices, and then we can just kind of ignore everything else and just focus on tracing those signals back and see where they get lost. We'll start by trying to write information to the DRAM. If you recall, then earlier on when I was trying to test this, I wasn't getting a write signal going to this particular device, and I suspect that it's actually addressable, but for some reason the first part of the test was failing. So what I'm going to start off by doing is connecting the scopes so that we can monitor the data going into the DRAM. So if we look at the data sheet, I've got the scope hooked up, so channels 1 and 2, that's the yellow and the blue channels, are on DQ1 and DQ2, so that's essentially bits 0 and bit 1. And channel 3 on the scope, the purple channel, is connected to the read-write line. So anytime that goes low, then we are writing data or trying to write data to the DRAM, and we should be able to tell by the activity on these particular lines whether we can successfully address this particular device. So the next thing I'll do is we'll point the camera at the Fluke, I'll enter a short program, and then we can see what the scope is picking up and whether we have an issue between the processor and the DRAM chip. So looking at the Fluke, I've got the Z80 pod plugged in, I've got the pod connected to the Wren main board, and what I need to do now is enter a simple program, and all I'm going to do initially is try to write repeatedly to the same address in the video RAM. Now that particular device that I've got the scope connected to is mapped to 8000 hex, so I'll write to an address somewhere in that range, and I'll write an alternating bit pattern so that we can try to ensure that we're actually seeing the data that we're writing rather than just random data. So I'll power up the Fluke. Apologies for any flickering on the display. And what I want to do here is just enter a program that will enable us to write repeatedly to the same address. So we'll create the program, and to start with I'm going to initialize 2 registers. So register 1 I'm going to set to the address I want to write to, and we'll use 8100 hex. And then register 2 I want to initialize to the value I want to write to that address. So if we pick an alternating bit pattern, so for example AA, so I now have the 2 registers initialized. I'm going to create a label so I can jump back to this point in the program, and I now want to write the value in register 2 to the address pointed to by register A. So if we write register 1, and we'll write to that address the value in register 2. And the final step in the program is to jump back to the label that we created. So go to label 1, and we'll just check the program, make sure it's entered correctly. So start the program, we initialize register 1, we initialize register 2, create a label, write the value in register 2 to the address pointed to by register 1, and then we jump back to the label. Okay, so all I need to do now is run this program, and we should be writing repeatedly to address 8100 hex, and we should be writing the value AA to that address. So I'll move the camera, I'll point it back at the Wren, and we'll see if we can detect that activity on the main board. Okay, as you can see I've got the pod connected to the Wren. I'll just move the camera so you can see the scope, and we're monitoring the first video DRAM chip. The scope is free running at the moment, and as I said, what we're looking at here is the yellow trace is data bit 0 on the DRAM chip, the blue trace is data bit 1, and the purple trace is the write enable line for that device. And you can see why we need to be specific in writing data to this device at the moment. There's just random information being picked up by the scope, and it would be very difficult for us to try and capture that. We could of course use the logic analyzer here to be specific in what we're triggering on, but I thought I'd show a slightly different technique this time. And so at the moment the program's not running. What I'll do is I'll start the Fluke up, and we should see the top line, which is the write enable line, going low briefly when the DRAM is written to. So I'll start the program, and as you can see that line is indeed going low. I'll do a single capture, and I'll now stop the program. So the program's now halted, and what we can see here is that the two bits we are picking up, the blue bit is a value of 0 and the purple is a value of 1, so we're getting 0, 1. What I'll do now is I'll change the line in the program that I had set as AA, and I'll change it to 5, 5 so that we are using the complementary values. So if we then run the program, we should see something different on the scope. So I'll just modify the program. Okay, I've modified the program. I'll start the scope running. I'll start the program. You can see it's running again. We'll do a single capture, and I'll now stop the program on the Fluke. And what you can now see is we're getting a value of 1, 0, which is the opposite of what we were getting last time. So I've changed the bit pattern so it's the opposite of what it was. So that looks correct. I'll just change the program back and see if it does successfully revert back to what we had before. Okay, I've modified the program. Start the scope again. Start the program. Do a single capture. I'll stop the program on the Fluke. And as you can see, it has changed back to 0, 1. And incidentally, I'm triggering the scope on the write enable pulse. So as you can see, we are successfully writing the correct value to that device. What I'm going to do now is check the other bits. So the DRAMs work in pairs. There are 2 for each 8-bit value. And what I'll do now is I'll go through and check that all 8 bits in both pairs are working correctly, make sure I can successfully write to those values, and what I'll do after that is extend the program that I'm running in the Fluke. So I will write a value and then read it back, and using this technique means that I can use the Wren itself to essentially decode and try to address and write to and read from those devices. And I'm hoping at some point I'm going to be able to determine exactly what the issue here, because this is all the Wren is really trying to do with this test that's failing. It's writing a value to the DRAM and trying to read it back, and for some reason that's failing. So if we're doing this from the perspective of the Z80, which is obviously where the Fluke is plugged in, then this should enable us to pick up the fault, and once I've picked up the fault and I know what it is, I can trace it back and try to find the cause. That's it for this video. In the next one I'll hopefully be able to show what I found as a result of this testing, and then we can go on and try to fix that fault and see if we can get any further through the self-test and further into the boot process.